So thank you all for coming here, and thanks to Google for the invitation to speak. Today I'll be talking a little bit about a new project that we're starting out on, which is supported by the NASA Health and Air Quality Applied Science Program, and it's aiming to create a data fusion tool for air quality estimation and forecasting using Google Earth Engine as our underlying system. I'm going to be presenting on behalf of the project team, which is listed here, including project PI Emma Noland. Before I get started, a little bit of motivation for why we care about air quality. And there are many reasons, but one of the key ones is the impact on human health. So this is some results from the Global Burden of Disease study, which aims to attribute basically causes of death to their underlying causes around the world. And according to the 2019 analysis, air pollution or poor air quality rather is responsible for approximately 7 million premature deaths annually, and that makes it the leading environmental risk factor for premature mortality. That's as opposed to behavioral risk factors, which are things like tobacco, smoking, and diet. So it's a major public health concern around the world. And with things like climate change, this is only projected to be an increased concern in the future. So that's why we kind of care about air quality, one of the main reasons. So how do we understand air quality? And there are a couple of basic resources we use to understand air quality, which I've tried to summarize on the slide here. At the top, you have things like more global data resources. These are things like global atmospheric chemistry models, which aim to simulate the dynamics of the atmosphere and the concentrations of different chemicals relevant for air quality. You also have things like satellite remote sensing data from different satellite instruments, which give us a good top-down overview of the air quality situation over a wide area. On the other side of the spectrum, you have more local resources. For example, several countries have regulatory monitoring networks which routinely measure air quality for basically regulatory enforcement purposes. And then you also have emerging networks of low-cost sensors, which, as the name implies, are a less expensive alternative to these regulatory equipment, which are sort of within the range where university groups and citizen and community scientists can get involved in monitoring their local community air quality with those kinds of instruments. So you have a range of different sources for air quality. But one of the problems or shortcomings we've identified is that there's really, to integrate all these different sources together, it takes a lot of time, effort, resources, which is sometimes beyond the capabilities of more casual users or even of local air quality managers who don't really have the resources to do this by themselves. So this project, which we're embarking on, is aiming to try to reduce that barrier a little bit by building a freely available online tool, which is relatively simple to use, to combine these different air quality data resources into a consistent platform. And for this project, we've chosen to use Google Earth Engine to implement this tool. And there's basically two main reasons for that. The first is that it's globally available and free to use, which is very important to allow people to use this resource. And then also the fact that many data sets relevant for air quality are already present on the Google Earth Engine system in some form. And this is only being expanded recently with a recent NASA-Google partnership, which I'll talk a little bit more about that later. But once this tool that we seek to develop is implemented, it will be able to provide estimates and near-term forecasts of air quality, which are relevant and applicable to a local scope. Think, for example, a good-sized city scale, but where the same underlying tool and method can be equally applied basically anywhere in the world that you have relevant data. So the outputs of this tool can also be post-processed in order to do things like warn of impending hazardous air quality events or track local changes in air quality over space and through time, and also to try to estimate our confidence in the air quality estimates based on what kind of information went into creating those estimates. And ultimately, we hope that the outputs and resources produced by this tool will be made available to the end users, basically local air quality managers and interested community scientists, to help them better understand and better visualize their local air quality situation, and from that understanding to hopefully take better actions to improve their air quality, both in the short term, in terms of avoiding potentially hazardous air quality, and in the longer terms, in terms of actually taking action to mitigate and reduce air pollution. We have a lot of partners on this project, which we've chosen to work with. They're listed on the slide here. Just a couple highlights. Our project co-I, Nathan Pavlovic, and his team from Sonoma Technologies are really going to be doing the actual implementation of the data fusion algorithms that we've developed in the Google Earth Engine platform. And that's based on their past experience doing similar work for air quality managers in the US and around the world. Also, we have our institutional partners, the UN Environment Program, UNEP, and the US EPA, who are going to help us coordinate with cities in the US and around the world who have agreed to help us with a pilot deployment and initial testing of this new tool as we develop it. And then at the end of the project, we'll be handing off the tool we developed to UNEP and US EPA for ongoing stewardship and to help new end users integrate it into their own air quality management and decision-making practices going forward. So just to briefly highlight, before I get into our project specifically, I want to highlight some of the data sets that are available in Google Earth Engine, specifically those from my office, which is the NASA Global Modeling and Simulation Office. That's where I work. So one data set we have, we're integrating into Google Earth Engine is the GOCF, that's the Goddard Earth Observing System Composition Forecast Model. And this is basically an integration of meteorological model outputs with a atmospheric chemistry module, and it aims to provide estimates and short-term forecasts, basically up to about 5 days in advance, of the chemical constituents and their concentrations in the atmosphere, including things that are relevant for air quality, like nitrogen dioxide, ozone, particulate matter, things like that. Another data set I want to highlight from our office, which is available in Google Earth Engine, is MERIT-2. That's the Modern Era Reanalysis data product. And this is basically a retrospective analysis which combines the global atmosphere model with satellite and ground-based measurement data to basically get the best estimate of the historical meteorological conditions around the world. And this also includes things like aerosol properties, which are relevant for air quality applications. So just two data sets I want to highlight from my office, which are available on Google Earth Engine or are being integrated into Google Earth Engine currently, and which might help you all with your research if you're doing similar work. So for the rest of my time, I'd like to give a little bit of a preview of the tool we're developing. This is based on basically a prototype version that we're working on. So it doesn't represent the finished product. It's still very much a work in progress, but hopefully it'll give you an idea of kind of how the system works and what it might look like once it's complete. For this demo, I'll be looking at the region around Dakar in Senegal, which is one of the cities we've partnered with to pilot this project. So the way we do this is we're going to start out with the atmospheric chemistry model as our baseline. So what I'm plotting here is the surface level nitrogen dioxide concentration from that model averaged over a 1 week period. So nitrogen dioxide is an air pollutant. It's typically emitted by vehicles and power plants and things like that. And it's relevant, especially in urban areas. You can see here the higher concentrations in and around the city of Dakar. So this is from the model, and you can see also here the resolution of the model as it compares to the size of the city of Dakar. So this is a fairly high resolution for a global model, but still it's only a few grid cells covering the whole city, so you're not getting a lot of spatial resolution from the model by itself. So we then bring in other data sources to inform us about that. For example, here what I'm showing is data from the European Space Agency's TRPOMI satellite instrument on the column concentration of NO2 in the atmospheric column. And you can see both the similarities in terms of the higher concentrations in and around the city of Dakar, but also the differences in terms of the increased spatial resolution, a little bit of noise in the data, and also some finer scale details that were kind of obscured by the model, but come out in this little bit of higher resolution data set. So the idea here is we'll take these data sets and we'll bring them together with other information from our model, like the column concentration of NO2 from the model, which is directly comparable to what the satellite's seeing. So we'll bring that together during this calibration period, and we'll use that to identify relationships between these different data sets during that calibration period, and then apply it to our application period. So what that means is that if we were going to, let's say, forecast air quality in the near future, we would take the underlying forecast from the GeoCF model system, which is shown here, and then we would impose those relationships we determined in the calibration period onto that forecast estimate, which would look something like this. So you can see the underlying trend is basically being forced by the model forecast, but we're also getting some information, especially on the variability of air quality below the resolution of our model, and that's mainly coming from the satellite data. If we had other data sources, we'd also integrate those. So for example, if we have regulatory air quality monitoring stations in the city of Dakar, as shown here, we would incorporate their data by, again, during that calibration period, looking for relationships between the model, satellite, and now the ground-based data sources. And then for forecasting, we would then extrapolate and extend those relationships into the future and apply them to the forecasting period and get an updated forecast, which would look something like this. Furthermore, if we had access to a low-cost sensor network in the area with potentially more sites than available with just the regulatory monitors, which is shown here, just zooming in a little bit on that, we would also incorporate those low-cost sensor data in a similar manner, but we would also want to do an additional step of calibration verification, and that's basically to verify that the low-cost sensors are, at least broadly speaking, in agreement with all these other data sources we have. That gives us more confidence in the data that are being provided by these low-cost sensors, and then we could incorporate them into the data fusion approach. So hopefully this has given you sort of a little bit of an idea of how this project, what the idea, the motivation for this project, how we envision it working, and a preliminary demonstration of the system we're developing in Google Earth Engine. A little bit now looking kind of on the temporal side as opposed to the spatial side. This is a time series plot. I won't go into a lot of detail, but just to know the solid green line there is the data from the regulatory monitoring station. That's basically the ground truth. In this case, this is a preliminary version, so I'm using synthetic data here. This is not the actual ground-based data. That's still being worked on, but just to give you an idea of how it might work once we have that integrated. So we have the regulatory monitoring data. That's basically the ground truth that we're trying to go towards. And you can see as we move from the model by itself in blue to the model and the satellite data together in orange, to the model, satellite, and now other ground-based data resources in purple, and then finally incorporating the localized low-cost sensor data in the green dotted line, we're moving kind of progressively closer and closer to that ground truth, at least in this example. So thank you very much for your attention. I think there's some time. If you have questions, I'm happy to answer them. And yeah, that's it. Yeah. Okay, so there's two questions. The first, I think I'll answer the second one first. So the second question was, how does satellite data get integrated into this approach? And the basic difficulty is that the satellite is measuring, as the questioner asked, the satellite is measuring what's happening usually in the column of the atmosphere or a significant portion of the column, versus what we're trying to estimate is really the ground level air quality where people are actually breathing. And the initial approach will be basically to use our model, which models both the column and the surface, to establish what that relationship is. And at least at first, we'll be making some assumptions that that's at least reasonably correct. We'll also, as I mentioned, be trying to quantify our uncertainty. So trying to get a handle on how correct that is in a given location and time, and putting some sort of error bounds on that. But that's going to be our first assumption, or our first approach, basically using the model to inform that relationship. And as the model improves in the future, we hope that relationship will improve, and then the underlying system will improve. And then the first question was how low-cost sensor data will be implemented into the project, whether we're looking at only one company or whether we're looking at low-cost sensor data generally. So for this project, one of our collaborators is from Clarity, which is a low-cost sensor provider. So we'll be, at least initially, focusing on the data that they provide to us. And then they have deployment, and then depending on the specific cities that we're working with in this project for the pilot deployment, we're going to be focusing on whatever low-cost sensors are sort of most prevalent in their areas as a first step. Now, that being said, through this project, we'll be sort of developing the methodology by which these low-cost sensors are incorporated. And I mentioned briefly we want to do calibration verification. We can also do a little at least to a little bit of an extent, a in situ calibration. So making some assumptions that on average over a relatively wide area, the low-cost sensors should be in agreement with the estimates from the model satellite and the regulatory monitors. We can develop at least a rough calibration to sort of correct the ensemble of low-cost sensors to better match that. And then any individual low-cost sensor that kind of is reading high or reading low with respect to that ensemble will provide information about what's locally happening in the vicinity of that low-cost sensor. I would say that's definitely one of the major things we're going to be working on implementing this project, and one of the sort of the unsolved parts of the project is how to pull the low-cost sensor data in a good and consistent way. So the question was, how are we going to validate especially the spatial heterogeneity of air quality from these data sets? And I think the basic tool will be, at least at the first stage, the basic tool will be the cross-validation approach. So we've picked a couple of areas of application which have, at least relatively speaking, a high density of ground-based measurements. And by individually or in clusters leaving sites out of the set of input data and then verifying against those left out sites, we kind of get a handle on how well is it capturing how well are we estimating for specific locations, and then digging into that results, we can say, okay, we're overestimating in these areas, underestimating these areas, that's where we need to do more work. So that's at the most basic level. And then, as I mentioned, as part of our uncertainty quantification, we do hope to be able to provide some kind of bounds on the estimates we give, so that you will kind of get a sense of, okay, this is the estimate, but it's relatively more or less certain in different areas, or depending on the level of, at high concentrations, we might have higher uncertainties. Maybe the relative uncertainty is the same, but the absolute uncertainty might be higher. So providing the end users both with the estimates themselves and with some metrics related to the confidence in our estimates, we hope to accurately convey the fact that we might not be capturing the spatial heterogeneity perfectly, but this is sort of our best range, our best guess. And then, hopefully, as we get better data sets and better high resolution satellite data, high resolution models in the future, those can sort of be swapped out of the system and improve it overall.